Welcome to the Deep Dive. Today, we're getting into chemigation.
That's right. Applying things like fertilizers, pesticides, agricultural chemicals through the irrigation system itself.
And our goal here is to really break it down for you. We want you to walk away knowing the pros and cons.
The different types of irrigation systems people use for this and why some might be better than others.
Exactly. We'll touch on drip systems specifically too and wrap up with the key things you need to weigh up before deciding if chemigation is right for you.
Okay, so let's start with the basics. Chemigation, fundamentally, is mixing those chemicals into your irrigation water.
And the big draw is that targeted application, isn't it? Being able to put chemicals just where you need them.
Precisely. You can control where they go, when they go on, and even how deep into the soil profile.
Plus the timing can be perfect. Maybe right after you irrigate anyway, or using that water to get soil-applied herbicides working.
Yeah, that activation aspect is important.
And think about the field itself. Less heavy machinery driving around.
Which means less soil compaction. That's a huge benefit for soil health in the long run. Better water intake, too.
Right. And less physical damage to the crops. Potentially safer for the operator, too. Less direct handling of chemicals.
Definitely. You can even sometimes apply when the field conditions are maybe too wet or unsuitable for a regular sprayer.
And you're not adding extra water just to get the chemicals worked in.
True. But it's not all positive. There are definitely drawbacks to consider.
Like the cost, I imagine. Getting set up.
Yeah, the initial investment can be significant. You need specialized injection pumps and, crucially, backflow prevention devices. Safety first.
Absolutely. Protecting the water source is paramount. Environmental contamination is a real risk if things aren't managed correctly.
It is. And another thing, especially with sprinklers, is drift.
Like center pivots. Wind can be an issue.
It can be. And overspray, too, if the irrigation pattern doesn't quite match the field boundary or the target zone. Those end guns on pivots, often a bad idea for chemigation because they're just not that uniform.
Okay, so that leads into what you need to think about before you even start.
Right.
What are those key decision factors?
Well, number one, check the pesticide label. It has to explicitly allow application via chemigation for that specific product. No exceptions.
Makes sense. What else? Location.
Location is critical. Think about proximity to buildings, roads, your neighbors' crops, any sensitive areas like water bodies. You might need setbacks.
And some chemicals have specific rules.
Soil fumigants, particularly. They often have quite strict buffer zone requirements you need to follow.
And the soil itself plays a role, right? How the chemicals move.
Hugely. Sandy soils, water and chemicals move through faster. Good infiltration, but you risk leaching below the root zone.
Okay. And clay soils.
They hold on to water and chemicals more tightly. Less leaching risk generally, but maybe the chemical doesn't move down as readily as you want. It's a balance.
And what about hills or uneven ground? Topography.
Yeah, with sprinkler systems, slope can affect the water pressure along the line. Different pressures mean potentially uneven water and chemical distribution.
Which brings us to the irrigation system itself. Uniformity sounds key.
It really is. You want that system distributing water and therefore the chemical as evenly as possible. We measure this with something called the uniformity coefficient, or UC.
And what's a good target UC?
You're aiming for 85% or higher for effective chemigation. If it's lower, especially with systems like traveling guns, you really need to manage them carefully or make adjustments.
So systems like center pivots or those linear move ones are generally pretty good for this.
Typically, yes. Their movement is usually consistent. The nozzles are designed for uniformity. They tend to have higher UCs.
What about other sprinkler types, like the hand move ones or side rolls, traveling guns?
They can be used, but often need more, let's say, careful management. Their uniformity might not be inherently as high due to how they're moved or pressure variations. And again, avoid those end guns for chemigation if possible.
Got it. Now let's switch gears slightly. What about drip irrigation? That seems quite different.
It is very different. Drip systems apply water and chemicals very precisely, directly to the root zone.
How? Through little emitters.
Exactly. Emitters or drippers, placed on the ground or even buried, they release water slowly, maybe just a gallon or two per hour per emitter. Or you can have higher flow types like micro sprinklers or porous tubing, very targeted.
Okay, so let's recap quickly. We've got definite advantages: precision, less compaction, timing, but also disadvantages: cost, environmental risks if mismanaged.
Right. And critical checks beforehand: the label, location, soil type, topography.
And for the system itself, uniformity is king, especially for sprinklers. Center pivot and linear move often do well there. Drip offers that super precise, direct-to-root application.
Understanding your specific system is just crucial for doing this safely and effectively.
Absolutely. So wrapping up, here's something for you to think about. Considering all these factors, especially the environmental ones and the need for precision, how might new tech, like advanced sensors and automation, change chemigation practices in the future? Could we get even more precise?
That's a great question. Imagine real-time soil moisture data feeding directly into the chemigation controller, adjusting rates on the fly. The potential is certainly there for further refinement.
Welcome to the Deep Dive. You're here because you want to get smart fast. And today we're diving into chemigation. That's applying pesticides through irrigation systems.
Right.
Think of this as your quick guide, the essentials pulled straight from a Wisconsin pesticide applicator training manual.
Exactly. We've gone through this manual, really pulled out the critical stuff you need to know. Our goal here is just to cut through the noise and give you the key regulations, the equipment you're going to know about, and the calibration steps, how to do it safely and legally.
And here's a really useful tip the manual itself gives. Pay close attention to those learning objectives. They're usually at the start of each chapter.
Yeah. Those are crucial.
Apparently, the certification exam is basically built around them. So if you get those objectives, you're pretty much set. Let's jump into Chapter 1, Introduction to Chemigation, and those objectives. First one, advantages and disadvantages. Okay, let's unpack that.
Okay, so why even do chemigation? Well, the manual points to the precision, You can match the pesticide application right to the water needed for a specific depth in the soil.
So it's more targeted.
Yeah, exactly. A more targeted approach. And another big plus is timing. You can sometimes apply pesticides even when, say, the field's too wet to drive equipment through.
That makes sense.
Plus, for some pesticides, that extra moisture from the irrigation actually helps them work better, helps activate them.
Right, get the right amount, right time, even if the ground's muddy. Okay, so what are the downsides, the catches? The manual mentions the upfront cost, right? The gear.
Yeah. That's a big one. It's definitely an added investment compared to just your standard irrigation setup. And a really significant concern is the potential for environmental contamination.
Getting into the water supply.
Exactly,
Right.
Especially water supplies. That's why the regulations we'll get into later are, they're pretty strict. Also, drift and overspray can be issues with certain sprinkler systems, the ones with wider spray patterns.
And I guess it's not always faster, is it? The manual says chemigation can sometimes take longer than other methods.
That's true. And you might end up watering even if the crops don't strictly need it right then, just to get the pesticide on.
Okay, the next learning objective asks us to think about the factors before you even decide to use chemigation. It's not just a simple decision then.
No, absolutely not. The very first thing you check, the pesticide label. It has to specifically say that application through irrigation systems is okay.
Seriously, that specific.
Oh yeah. The manual really hammers this home. If the label doesn't approve it, you just can't do it, period. Then you've got to think about your location, where you are in relation to sensitive areas.
Like houses, schools.
Exactly. Homes, schools, lakes, rivers, wells, those all need careful consideration. And soil fumigants, they have especially strict buffer zone requirements.
So protecting people, protecting the environment around the field. What about the field itself? Soil type must matter, how well it takes water.
For sure. Sandy soils, for instance, might let water and pesticides move down too quickly. You risk leaching below the root zone.
Right, and clay.
Clay soils can be the opposite. If you apply water too fast, you get runoff. And then there's topography. Uneven ground can mess with the pressure in sprinkler systems, leading to uneven application.
Okay.
And finally, the manual really stresses knowing your irrigation system's characteristics, particularly how uniformly it applies water. They measure this with something called the uniformity coefficient, or UC.
Higher is better.
Yep, a higher UC means more even water distribution, and that's absolutely key if you want consistent pesticide application.
Okay, that leads right into the next objective, the types of irrigation systems used. The manual focuses on sprinkler and drip systems, at least in Wisconsin. Can you give us some examples?
Sure. For sprinkler systems, the manual lists the common ones. You've got center pivot, linear move, solid set, hand move, side roll, tow line, and even traveling guns.
Okay, and drip.
Drip systems are simpler conceptually. Just a network of emitters delivering water slowly right to the root zone. Interestingly, the manual does note that some really specific pesticide labels, especially for fumigants, might actually only allow application through drip irrigation.
Huh. Good to know. And the next learning objective asks why some sprinkler systems are better than others for this. Sounds like that uniformity thing again?
Exactly. It comes back to uniformity. The manual generally favors center pivot and linear move systems because they tend to give you a more consistent, even application of both water and pesticide across the whole field.
Makes sense.
But there's a fascinating point about water-driven center pivots. The application rate can actually be higher right around the drive towers, so that can lead to unevenness too.
Oh, right.
And a really crucial point, end guns. On any sprinkler system, you have to manage those end guns super carefully to avoid spraying outside your target area. In fact, the manual says if you're using fumigants, end guns are totally prohibited.
Wow, okay. That's a hard stop. Especially with those more volatile pesticides. The last objective for Chapter 1 is about drip systems. Sounds like they fill a specific role.
They really do. Because drip applies water so slowly and directly to the soil, right at the roots, it's perfect for getting things like fertilizers and herbicides exactly where they need to be. The manual notes the emitters can be on the surface, above ground, or even buried.
All right, Chapter 1 done. Let's move to Chapter 2, Chemigation regulations. First, learning objective. Who actually needs to be certified to do this? It's not just anybody, is it?
No, definitely not. It's quite specific. According to the manual, you need Chemigation certification if you're a private applicator, say, a farmer using restricted use pesticides or RUPs.
Those are the ones with tighter controls.
Right, because of potential hazards. The same goes for commercial applicators who aren't for hire, like maybe someone working for a food processor if they're using RUPs. Now, if you're a commercial applicator for hire doing Chemigation with any pesticide, RUP or not, you need the certification. And finally, anyone, absolutely anyone, applying any pesticide via Chemigation on school grounds needs to be certified.
That covers a lot of ground, especially around schools. And this Chemigation cert is usually an add-on, right? You need a base certification first.
That's exactly right. You typically need to be certified in a relevant base category first, like general farming or maybe field and vegetable crops, before you can add the Chemigation subcategory.
And what about those fumigants again?
Yes. If you're applying soil fumigants through Chemigation, the manual says you need yet another specific subcategory, soil fumigation. So yeah, depending on what you're doing, the certifications can definitely stack up.
Wow, really underscores the responsibility.
Yeah.
Okay, next objective. What the pesticide label itself has to say. It's not enough that the product is just generally approved for use.
No, not at all. If a pesticide can be applied through irrigation, the label will have very specific instructions. It'll list restrictions, how to do it, and crucially, which types of irrigation systems are allowed.
And which aren't.
And which are absolutely prohibited. Yes, the manual is crystal clear. If the label doesn't mention Chemigation, or if it specifically forbids it, you cannot use that pesticide in your irrigation system. You just can't. Always read the label front to back.
Seems non-negotiable. Okay, the third learning objective here focuses on ATCP 29. That's Wisconsin state regulation, specifically about protecting the water supply. Given the risks we talked about, this sounds vital.
It's absolutely critical. The manual stresses you cannot directly connect your Chemigation setup to a public drinking water supply without some serious safeguards. You need to prevent contamination.
How do you do that? What are the options?
There are basically two main ways. One is a physical separation called a vertical air gap. The manual says this needs to be at least 2 feet high or twice the diameter of the water outlet pipe, whichever is greater.
A physical gap, okay. What's the other way?
The other is using approved mechanical backflow prevention devices.
Like those reduced pressure principle backflow preventers. The manual mentions specific standards they have to meet.
Yes, exactly. They need to meet ASCII standard 101380. And importantly, these mechanical devices have to be tested every year by a certified tester, make sure they're working right, and you have to protect them from freezing, of course.
Right.
The manual also briefly mentions things like barometric loops, double check valves, and a check valve plus a gooseneck loop, but it really advises checking the actual legal text for the full details on those.
Good advice. Always go to the source for the fine print. Moving on, the next learning objective is about posting warning signs. When do you need to put those up?
You have to post warning signs if any part of the area you're treating is within 100 feet of a public road or within 300 feet of what they call sensitive areas.
Okay.
Homes, schools, hospitals, public parks, places like that. The whole idea is to alert people who might be nearby.
And there are rules about timing and what the signs look like. Can't just be any old sign, I imagine.
Nope. They have to be posted before you start chemigating, and you can only take them down after the application is done and any treated surfaces, like plant leaves, are dry. The manual even specifies letter size minimum 2.5 inches high, and the stop sign symbol needs to be an 8-inch octagon.
Where do you put them?
You need one every quarter mile along the border that faces the road or the sensitive area, and also at all the usual entry points to the treated field.
Okay. The next objective shifts to the Chemigation System Operation and Observation Plan. Sounds like a formal document.
It is. Before you operate a chemigation system, the manual says you have to prepare a written plan. It details how you'll run the system and how you'll watch it. And you have to follow that plan every single time you chemigate.
Where do you keep it?
Copies need to be accessible, one at the application site itself or with the operator during the application, and another copy needs to be at your main place of business or residence or the property owners.
And do you actually have to be there the whole time it's running?
Well, the manual says an operator must be physically present at the site whenever there's a potential for drift or overspray onto those sensitive areas defined in your plan.
Okay. And if sensitive areas aren't nearby?
Even then, you still need to visit the site at least once every hour, just to check that everything's running correctly, as planned. And it's worth noting, these rules are even stricter if you're using certain soil fumigants.
Right. Okay, next objective. The specific equipment requirements for the system itself in Wisconsin. We touched on backflow prevention, but what else is legally required?
Yeah, the manual gets detail here, all for safety and environmental protection. First, anything that touches the pesticide tanks, hoses, fittings must be made of materials that resist corrosion, puncture, and cracking.
Makes sense.
And crucially, these materials have to be chemically compatible with the pesticides you're using. You actually need written confirmation of this compatibility from the manufacturer, and you have to keep it on file.
Wow, okay. What else?
The area where you handle the pesticide concentrate, like near the supply tank and injection point, needs to be at least 8 feet away from any water supply, well or surface water. And it must have secondary containment.
To catch spills.
Exactly, to capture any spills or leaks before they can get anywhere.
What about automatic safety stuff? Shut-offs.
Yes, several mandatory automatic systems. There has to be an automatic low-pressure shutoff for the irrigation system. If the water pressure drops too low, the whole system stops. Prevents applying pesticide without enough water.
Okay.
Then there's the pump interlock. This links the water pump and the pesticide injection pump. If the water pump stops for any reason, the pesticide pump has to automatically shut off too.
Ah, so no injecting pesticide into dry pipes.
Right. Plus, you need a flow interrupter in the pesticide supply line, and either a flow sensor or a pressure switch in the injection line itself. These are designed to stop the pesticide flow if the injection pump fails or if there's a break in the line.
Lots of safeguards.
One more key one. A spring-loaded check valve, minimum 10 psi opening pressure right in the injection line. This specifically prevents irrigation water from flowing backward into the pesticide supply tank. It's definitely a multi-layered safety approach.
Really hammers home that prevention of backflow or siphoning. Okay, the final learning objective in this chapter deals with medum, sodium, and chloropicrin. Very specific restrictions here. Sounds like these need extra care.
They absolutely do. They reflect the higher potential risks with these soil fumigants. For these, you have to provide a 72-hour advance written notice to both the county public health agency and all residents living within a quarter mile of the application site. And this notice has to include specific details, what you're applying, when, potential exposure symptoms, contact info.
Wow.
Plus, residents have the right to request pre-application info directly from the applicator, and the applicator is obligated to provide it.
And during the actual application, or rules.
Yes. A certified applicator must be physically present at the chemigation site at all times during the application of either medum sodium or chloropicrin. No leaving the site.
Okay. Weather restrictions too.
Yep. Strict weather limits. For medum sodium, you can't apply if the air temp is over 80 degrees Fahrenheit or if the soil temp down at 5-6 inches is above 70 degrees F. There are also rules about rainfall after applying medum sodium. Wind speed limits come into play too, and they vary based on nozzle type, height, pressure.
And the end guns.
And like we mentioned before, end guns on sprinklers are absolutely prohibited when applying these specific fumigants. No exceptions.
Okay, that paints a very clear picture of the regulations in Wisconsin. Let's shift gears now to Chapter 3, Chemigation Equipment, first learning objective. What are the two main goals behind how chemigation equipment should be designed?
The manual boils it down to two fundamental goals. First, Effective and uniform application, getting the right amount of pesticide spread evenly across the target area.
Okay.
Yep.
And
Second, and just as critical, protecting the water supply from contamination by the pesticides. Every single component, every connection should really serve one or both of these goals.
makes sense. The next objective asks for 3 materials, generally okay for pesticide supply tanks. What are they usually made of?
The manual lists stainless steel, fiberglass, and polyethylene plastic. These are picked because they resist corrosion from a wide range of chemicals.
What about mixing? Agitation?
Good point. The manual mentions agitation too. Sometimes hydraulic agitation, just circulating the liquid, is enough. But often, especially for wettable powders or flowables, you need mechanical agitation, like paddles, to keep the product properly mixed. As always, check the pesticide label for specific recommendations.
Right, the label rules again. Objective 3 highlights why knowing your injection pump's capacity is so important. Why is that?
It's crucial for consistency. You need to make sure your pump can actually deliver the rate you need, and you want to operate it within its best range, not pushing it to its absolute maximum or running it down at its minimum output.
Why not the extremes?
Well, operating at the extremes can damage the pump, for one, but it can also lead to inaccurate pumping rates. The manual specifically flags that piston-type pumps can sometimes lose suction if you try to run them at really low output settings.
Okay. The next objective talks about why diaphragm injection pumps are often preferred. What's good about them?
Diaphragm pumps have a few nice advantages for chemigation. They tend to have a simpler design, fewer moving parts compared to other types. That usually means less maintenance and, importantly, less risk of leaks.
Which is good for safety and the environment.
Exactly. Minimizes potential exposure. Also, the pesticide itself only really contacts the diaphragm and the check valves, which reduces issues with corrosion inside the pump. And a big plus for calibration, you can usually adjust the injection rate pretty easily while the pump is running.
That ease of adjustment sounds really helpful for dialing in the rate. Okay, next up. Venturi injection units. How do they work? How do they pull a pesticide in?
Venturi units work on a cool fluid dynamics principle. They basically create a pressure difference of a vacuum using the flow of the irrigation water itself. There's a narrowed section, the venturi. As water flows through it, it speeds up and the pressure drops.
Okay.
That lower pressure then sucks the pesticide solution from the supply tank right into the main irrigation water stream.
How do you control how much it sucks in?
You control the injection rate, essentially the strength of that vacuum, usually in one of 2 ways. Either with a pressure-reducing valve put in the main irrigation line just before the venturi, or sometimes by using a small extra pump called an auxiliary or booster pump connected up with the venturi to increase that pressure difference.
So it uses the water flow itself. Interesting. Now, compare those injection pumps to greenhouse proportioners. The manual contrasts them. What's the key difference?
The main difference is how they measure out the chemical. Injection pumps, like the diaphragm pumps, are set up to deliver a specific calibrated amount of pesticide over a certain time, like gallons per hour.
Okay, and proportioner.
Greenhouse proportioners typically work differently. They deliver the pesticide based on a fairly constant proportion or dilution ratio relative to the water flow. So if the water flow rate goes up or down, the amount of pesticide injected also goes up or down to maintain that ratio. An injection pump, though, aims for a steady volume per hour, mostly regardless of small changes in water flow.
That's a pretty important distinction for field applications where you want a specific rate per acre.
The next objective asks for the 4 main types of greenhouse proportioners mentioned.
Right. The manual lists 4 common ones for greenhouse use. Venturi types, which work on that same pressure difference principle we just discussed. Displacement diluters, where incoming water physically pushes out a set amount of concentrated pesticide. Positive displacement pump proportioners, using a small pump that injects a fixed amount per stroke. And EC injection units.
EC.
Electrical conductivity. These monitor the conductivity of the water fertilizer mix and adjust the injection rate automatically to keep it at a target level. Pretty sophisticated. Now, something we haven't discussed, the calibration tube. Next objective. What is it? What's it for?
Okay, a calibration tube. It's usually a clear tube, plastic or glass, marked with volume measurements like milliliters or ounces. It's installed in the pesticide supply line, right between the main supply tank and the injection pump.
And its purpose.
Its main job is to let you visually measure exactly how much pesticide the injection pump is putting out over a set period of time. Use it during calibration, obviously, but also you can use it to double-check things during the actual application.
How does that help?
By timing how long it takes for the liquid level in the tube to drop a certain volume, you can calculate the actual injection rate, say, in ounces per minute. Then you compare that to the rate you calculated you need, and you adjust the pump setting up or down until they match. The manual says it should be big enough to measure accurately over at least 5 minutes.
Makes sense. Need a decent time window for accuracy. Okay, critical safety issue next. The 3 main ways the water supply can get contaminated if things go wrong.
Yeah, the manual flags 3 key bad scenarios. First is backflow. The pesticide mix in the supply tank flows backward into the water supply. This happens if the main irrigation pump stops, but your backflow prevention isn't working or isn't there.
Okay, that's bad. What else?
Second is also backflow, but kind of the reverse. Irrigation water flows backward into the pesticide supply tank. This can happen if the injection pump stops working, but the main irrigation pump keeps running, dilutes your mix, potentially overflows the tank.
Also bad. And the third?
The third is siphoning. This is where the pesticide mix already in the irrigation pipes gets sucked back into the water source, like a well or pond. This can happen if both the irrigation pump and the injection pump shut down at the same time, especially if there's a pressure drop.
These scenarios really highlight why those anti-pollution devices are so crucial. Which brings us to the next objective. Describe the purpose and function of these safety components.
Right. These devices are designed precisely to stop those contamination nightmares. The main backflow preventer, often that reduced pressure principal assembly, uses check valves and an atmospheric vent port to create a physical barrier against both backflow and backsiphoning.
What about for surface water, like ponds?
For surface water sources, the manual mentions using a combination of check valves, vacuum relief valves, and low-pressure drains to get similar protection against backflow and siphoning. Then you have the pump interlock we mentioned that stops the injection pump if the water pump fails.
Right.
The flow interrupter and the flow sensor in the pesticide line act as fail-safes if the injection pump itself messes up or a line breaks. And finally, that injection line check valve, the one needing 10 psi to open, that's specifically there to stop irrigation water pushing back into the pesticide tank. It's really a system of checks and balances.
Definitely sounds comprehensive.
Yeah.
Last objective in this chapter. The freshwater faucet sometimes found on these systems. Where should it be? What's it for? And what protection does it need?
Okay, if you have a freshwater faucet on the system, it must be located upstream of the main backflow prevention device. Before it.
Why have it?
Its purpose is usually for things like cleaning equipment, rinsing out empty pesticide containers, maybe filling the pesticide supply tank with clean water to mix the pesticide. But, and this is critical, you have to prevent any chance of backflow from this faucet back into the clean water supply line.
How?
Usually with a hose bib vacuum breaker fitted onto the faucet, or by using a faucet that has backflow protection built right in. The manual also stresses that this faucet should be clearly labeled non-potable, not safe for drinking, and you should absolutely never use it for injecting pesticides or obviously for drinking water.
Got it. Okay, we've nailed the equipment. Let's talk chapter 4. Calibration, getting the amount right. First objective, list the 6 basic steps for calibrating any chemigation system.
All right. The manual lays out a pretty logical 6-step process. Step 1, figure out the exact size of the area you're treating. Acres, usually.
Step 1, area.
Step 2, know your target pesticide rate. How much product per acre? That comes from the label.
Step 2, rate.
Step 3, calculate the total amount of pesticide needed for that whole area. Just multiply area by rate.
Step 3, total pesticide.
Step 4, decide on your injection time. How long will you run the injection pump?
Step 4, injection time.
Step 5, calculate the required injection rate. How fast does the pump need to run? Usually gallons per hour or liters per hour. You get this from the total pesticide needed divided by the injection time.
Step 5, injection rate.
Okay. And finally, step 6, adjust your injection pump setting to actually deliver that calculated rate. This is where the calibration tube comes in handy.
Step 6, set the pump. Okay, area, rate, total pesticide, injection time, injection rate, set pump. Got it. The next 3 objectives ask us to walk through these steps for specific systems. Center pivot, stationary sprinkler, and drip. Let's start with calibrating a center pivot.
All right, center pivot, assuming it does a full circle. Step 1, area. Calculate the area of that circle using the radius, the length of the pivot out to the last watered spot. Use the Pierce squared formula.
Okay, area calculated.
Step 2, rate. Get that from the pesticide label. Step 3, total pesticide, multiply area times rate. Step 4, injection time. This is usually the time it takes for the pivot to make one full revolution.
How do you figure that out?
You need to know the circumference of the path the outermost tower travels and the travel speed of that tower. Speed might be on a chart, or you might have to measure it. Time equals distance divided by speed.
Right. So now we have injection time.
Step 5, injection rate. Divide the total pesticide from step 3 by the injection time from step 4. This gives you, say, gallons per hour. Step 6, set the pump. Make an initial guess based on the pump specs, maybe set it to a certain percentage, then use your calibration tube.
How exact?
Time how long it takes to pump a known volume from the tube. Convert that measurement into gallons per hour, or whatever units you used in step 5. Compare it to your target rate, adjust the pump setting, and measure again. Repeat until it matches.
So for pivots, getting that area, and especially the revolution time accurate, is super important. Okay, what about stationary sprinkler systems, fixed positions?
Stationary systems. Step 1, area. This is usually calculated based on the spacing between the sprinkler heads on a line and the spacing between the lines themselves times the length of the lines being used.
Got it.
Step 2, rate from the label. Step 3, total pesticide, area times rate. Step 4, injection time. Here you have more flexibility than with a pivot. You might choose to inject only during part of the total irrigation cycle.
How do you figure out the total irrigation time first?
You need the system's water application rate, inches per hour usually. This is calculated from the flow rate of each sprinkler head, gallons per minute, and the sprinkler spacing. Then, based on how much water you want to apply, say half an inch, and the system's efficiency, it's never 100%,
Right.
You calculate the total time the sprinklers need to run.
Then you decide when to inject within that time.
Exactly. You might inject during the middle third or the last half, whatever the label suggests or fits your goal. So your injection time is just that portion you choose.
Okay.
Step 5, injection rate. Total pesticide, step 3, divided by your chosen injection time, step 4. Step 6, set the pump. Same process as the pivot, use the calibration tube, measure the output, adjust the pump until the measured rate matches the calculated rate.
So with stationary, you get that flexibility on when to inject during the watering. Could be handy. All right, last one. Calibrating drip or trickle systems.
Drip systems. Step 1, area. Use the total field area being irrigated, even though the water is only hitting narrow bands or spots. Step 2, rate. This often involves calculating a banded application rate. Because you're not treating the whole surface, the rate per treated acre might be higher than a broadcast rate. The label or guidelines should explain how to calculate this based on emitter spacing and row spacing.
Okay, a banded rate.
Step 3, total pesticide. Multiply that banded rate by the total field size from step 1. Step 4, injection time. This relates to the total irrigation time needed. First, figure out your system's application rate in gallons per hour per acre. You need the average flow rate per emitter, measure a few, and the number of emitters per acre.
Okay, that gives you gallons per acre per hour.
Right. Then, based on how much water you need to apply, say equivalent to a quarter inch of rain, you calculate the total irrigation time needed. Your injection time will usually be most of this irrigation time, but you need to allow for flushing at the end. Step 5, injection rate. Now here, you often calculate the total volume of pesticide mix you need, pesticide plus water in your supply tank, and divide that by your injection time. Step 6, set the pump. Again, use the calibration tube to fine-tune the pump setting to match that calculated injection rate. And the manual really stresses flush drip systems thoroughly after injection.
Right, flushing seems extra important for drip. Okay, next objective asks about factors linking the injection pump setting and the travel speed for a center pivot. Sounds like they're tied together.
Oh, definitely. They're very interconnected. You're trying to hit that sweet spot between the pesticide application rate you want, gallons per acre, and your pump's ability to deliver it evenly. Changing the pivot's travel speed directly changes how much water is applied per acre.
Faster speed means less water.
Exactly. Faster speed, less water, and potentially a thinner application of the pesticide if the injection rate stays the same. Slower speed, more water, thicker application. So you have to calibrate the injection pump at the specific travel speed and operating pressure you plan to use for the actual chemigation. You can't calibrate at one speed and then run it at another.
Makes perfect sense. Final objective in this chapter. Advantages and considerations for injection timing with stationary sprinkler and drip systems. We touched on this.
Yeah, the big advantage is that flexibility. You can choose when in the irrigation cycle to inject. For example, with a herbicide that needs to get into the soil, you might inject it, then run clear water afterwards to wash it in.
Or for something on the leaves.
Right. For a foliar, insecticide, or fungicide, you might inject it near the end of the irrigation cycle so you don't immediately wash it off with lots more water. But the main consideration is always flushing. You absolutely have to run clear water long enough afterwards to flush all the pesticide out of the entire system, pipes, laterals, everything.
And especially drip systems need thorough flushing.
Yes, particularly drip. Those small emitters are easily clogged, so you need to flush long enough to ensure clean water reaches the very last emitter on every line. Could take quite a while on large systems.
Okay, calibration covered. Let's wrap up with the final chapter, Chapter 5, Chemigation Management, Best Practices for Running and Maintaining the System. First objective, steps before and during application to make sure everything's working right.
Okay, before you even turn anything on, the manual says do a thorough walk-around inspection. Check all your hoses, clamps, fittings, look for leaks, cracks, wear and tear.
What specifically should you check?
Pay close attention to those safety devices.
Yeah.
The main line check valve, the injection line check valve, the vacuum relief valve, the low-pressure drain. Make sure they look okay and seem functional. Test the pump interlock if you can. Inspect the strainer on the injection system. Make sure it's clean. Check the water pump, the power source.
Okay, that's the pre-check. What about during the application?
During the run, it's all about monitoring. Keep an eye on pressures, flow rates. Listen for any weird noises from the pumps or motors. Watch the sprinklers or emitters to make sure the pattern looks normal. Basically, be vigilant for anything that seems off. The manual also suggests keeping the equipment area clean and tidy. And if you have sprinkler nozzles near sensitive areas, maybe plug them just to be safe.
For good tips. Next objective, flushing the equipment after use. When and for how long?
Flushing is crucial. Do it immediately after every single chemigation application while the irrigation water is still running. That way, the rinse water gets applied properly to the treated area.
How long do you flush?
The minimum recommendation is to flush for at least the time it takes to completely fill the entire irrigation system with fresh water. But, as we said, some systems, especially drip or micro-irrigation, might need much longer flushing times to really clear everything out.
What if the system shuts down unexpectedly?
If you have an automatic shutdown during chemigation, you should flush the system as soon as you find out it's stopped. And you might need to flush for longer than usual, just to be sure.
Clogging, big issue, especially for drip. Next objective, steps to prevent it.
Yes, preventing clogs is key for drip. The manual suggests several things. First, try to use pesticides that are known to be pretty soluble in water. Avoid things that settle out easily.
What about mixing chemicals?
If you plan to mix 2 or more chemicals in your tank, definitely do a jar test first. Mix small amounts in the same proportion in a clear jar and see if they react badly, form clumps, sludge, anything that could block emitters.
Good idea.
Also, make sure the products you choose aren't known to be corrosive or damaging to your specific system components, emitters, tubing, etc. And a really important tip for drip, inject the chemical before it goes through the main system filter.
So the filter catches any junk.
Exactly. The filter can then remove any little undissolved bits or precipitates before they reach those tiny emitters and cause blockages. And remember, water quality itself can cause issues, so compatibility tests are always wise.
Okay, final learning objective for our deep dive. How to reduce or prevent problems like drift, overspray, runoff, and deep percolation. Minimizing environmental impact.
Absolutely key. For drift, the main advice is don't chemigate when it's too windy. Generally, keep it below about 10 miles per hour wind speed. If possible, using sprinkler heads that are closer together and operate at lower pressures can also help.
Timing matters too.
Yes, chemigating at night or in the early morning when winds are usually calmer can make a big difference. For overspray, it's mostly about managing those end guns on pivots or watching the edges of stationary systems. Adjust them or shut them off so you're not spraying outside the target field boundaries.
What about runoff and water going too deep?
That's usually about applying too much water overall. So good irrigation management throughout the season is the foundation. Don't overwater generally. For center pivots specifically, you can increase the travel speed to apply less water in one pass. If you do see runoff starting, you need to manage it so it stays within the treated field. Maybe build berms at the edge.
And surface water.
And finally, the manual explicitly says avoid chemigating fields that actually contain ponds, streams, or other surface water bodies to prevent direct contamination.
Wow. Well, that was definitely a comprehensive deep dive into chemigation, wasn't it?
Yeah.
All straight from that Wisconsin pesticide applicator training manual. We covered a ton.
We really did. From the basic pros and cons all the way through the detailed regulations, the equipment, the calibration steps, and the management side.
It's clear there's a lot more to it than just dumping pesticide into the irrigation water. Understanding those learning objectives really does seem to be the path to getting the essentials down. And, like the manual hints, probably passing that certification exam.
Exactly right. Hopefully you, the listener, now have a much stronger grasp of the principles for doing chemigation safely and effectively based on this official training material.
And maybe a final thought to leave you with as you process all this. Think about how these really specific, detailed rules and guidelines we've discussed today show that constant balancing act, right, between needing efficient agricultural practices and our absolute responsibility to protect the environment and keep people safe. Perhaps this deep dive makes you curious to check out the specific regulations and best practices right where you are. Thanks for joining us for this in-depth exploration. Welcome to the deep dive. Today, we're getting into something pretty important: chemigation equipment.
That's right. How we apply pesticides effectively, but also critically, how we protect our water supplies while doing it.
Exactly. We're using Chapter 3 from a source that really goes deep into this. It's all about the gear, the hardware.
And our mission today, basically, is to break down these systems, understand the components, how they function, and the safety side of things.
Okay, so the chapter sort of lays out a roadmap first, doesn't it? Gives us the learning objectives.
It does. It sets the scene, tells you what goals drive the design, what materials work for the supply tanks,
Right.
why pump capacity is such a big deal, why diaphragm pumps often get the nod,
What else is on the list?
how Ventura units work, that pressure trick they use, the difference between injection pumps and those greenhouse proportioners,
Okay.
calibration tubes, why they matter, and then the big one, how water can get contaminated, and crucially, the anti-pollution gear designed to stop that.
And faucets too, right?
Yep.
Freshwater faucets.
Yep.
Where they go, what they're for, and how they need protecting. It's a pretty thorough list.
So let's dig in. The core goals of all this equipment. Seems like there are two main things driving it all.
Absolutely. First is getting the job done right, applying the precise amount of pesticide, nice and uniformly, over the target area. You need that consistency.
Makes sense. For effectiveness.
Exactly. But the second goal is just as vital, maybe even more so, protecting the water supply, making sure those chemicals don't end up where they shouldn't. And like you said, that's often a legal requirement.
Yeah, you definitely don't want contamination.
So those two things, uniform application and water protection, they really shape everything about the equipment.
Okay, let's start where the chemical starts. The supply tank. What are the key things there?
Material, first up, got to be non-corrosive. The chapter points to stainless steel, fiberglass, polyethylene plastic, stuff that won't react.
Right, and keeping the mix consistent, like stopping things from settling out.
Good point. Agitation? Sometimes just the liquid moving around hydraulic agitation is enough.
Sometimes.
Yeah, for some formulations. But often, especially if stuff tends to settle, you'll need mechanical agitation, like a stirrer.
And the label's the final word on that?
Always. Check the product label. It'll tell you exactly what kind of mixing you need.
Got it. Moving on to what the chapter calls the heart of the system, the injection pump. Sounds critical.
It really is.
Yeah.
This is what meters the pesticide into the water. Accuracy here is everything. We're aiming for like plus or minus 1% accuracy within its normal working range.
Wow, that's precise.
It needs to be. Get the dose right. Avoid waste. Avoid undertreating. Plus, they need to be easy to adjust, for different chemicals, different rates.
Like setting a dial.
Pretty much. And you need the right size pump for the job. Don't get one that's way too big or way too small for your typical needs. They're often marked maybe in percentages of total capacity or in actual volume units.
And the chapter warned about running them at the extremes, max or min output. Yeah, that's a definite no-no. Can cause damage or just mess up the accuracy. Piston pumps in particular can apparently struggle to suck up liquid properly if you're asking them to pump tiny amounts. Best to operate in that kind of middle sweet spot.
And cleaning, I imagine that's vital with these chemicals.
Oh, absolutely essential. Clean it thoroughly right after you use it. Leftover pesticide, that's just asking for trouble. It'll eat away at seals, hoses, shorten the pump's life, cause leaks. Bad news.
Okay, so types of pumps. Diaphragm, piston, venturi. The chapter seems keen on diaphragm pumps.
Yeah, they're often seen as the best all-around option for pesticides. Fewer moving parts is a big plus.
Less maintenance.
Less maintenance, fewer chances for leaks. And the design keeps the pesticide away from a lot of the internal bits, so less corrosion too. Just generally more reliable for this kind of work.
And easy to adjust the rate, you said.
Usually, yeah. They often have this micrometer-style knob. Makes it simple to dial in the exact injection rate you need. Good control.
What about piston pumps then? They exist, they're used.
They do. And they come in lots of sizes, which is why you see them used a lot for fertilizers, things that need higher injection rates sometimes.
But drawbacks for pesticides.
The seals can wear out faster, apparently. That means more upkeep, higher risk of leaks eventually. And calibrating the older ones used to be, well, a bit of a pain.
How so?
You'd have to stop the system, fiddle with the stroke length, start it up, check the rate, stop again, repeat till it's right. Though the chapter does say newer ones can often be adjusted while running, which is much better.
Okay. And the third type? Venturi units. How do they work?
They're different. They use a pressure difference. Like they create a low pressure area in the water line, and that vacuum basically sucks the pesticide in.
Clever. How's the pressure controlled?
Usually with a pressure-reducing valve in the main line, or sometimes a little helper pump.
And the main appeal is cost.
Yeah, that's their big advantage. Generally lower upfront cost than the mechanical pumps.
Right. Now, proportioners. These are mentioned mainly for greenhouses.
That's right. They're designed to mix concentrated stock solution, often fertilizers or fungicides in greenhouses, into the water at a set ratio.
A ratio, not a specific flow rate.
Exactly. Like the example 1 to 100. 1 part chemical, 99 parts water. The key thing is they maintain that proportion, even if the overall water flow changes.
So if more water flows, it injects more chemical to keep the mix the same.
Precisely. The injection rate varies with the water flow to keep that dilution constant. The chapter mentions a few types: venturi, displacement, positive displacement, and these EC injection units that monitor electrical conductivity.
EC units.
Yeah, I think hydroponics maybe. They measure the conductivity of the water, which relates to nutrient levels, and adjust injection based on that. Pretty smart for fine-tuning.
Okay. Let's talk calibration tubes. Sounds simple, but important for accuracy.
Definitely. It's just a clear tube, usually sits between the supply tank and the pump.
So you can see the pesticide.
Exactly.
Yeah.
You use it to measure how much the pump is actually putting out over a set time. You watch the level drop.
During setup and during the run.
Both. Essential for calibrating accurately and for checking things during the chemigation itself. Needs to be clear, tough, big enough to measure for at least 5 minutes, and have clear volume marks.
Right. Now, the really crucial stuff, anti-pollution and safety. Contaminating water is the big fear here.
It's the absolute top priority to prevent. The chapter lists ways it could happen: backflow from the tank, pump running when it shouldn't, back siphoning.
Scary stuff.
Which is why, as mentioned, places like Wisconsin legally require these safety devices. It's non-negotiable.
First up, the backflow preventer. Where does that go?
Upstream of the injection point, before the chemical gets added, the one described as a reduced pressure principle type.
How does that work, basically?
Think of it like 2 check valves in a row with a drain in between. If water tries to flow backwards, the valves stop it. And if there's any leakage or pressure issue, the drain vents it safely out. It protects against both backflow and back siphoning. It's a key line of defense.
And that drain needs to be positioned carefully.
Yes. Discharge has to go to the ground, away from the water source, and the outlet needs to be high enough off the ground, twice its diameter, to prevent any chance of siphoning back into the drain itself.
Okay. Then there's a check valve and vacuum relief valve setup.
Right.
For surface water sources.
Right. If you're drawing from a pond or a river, this combo stops the pesticide mix draining or siphoning back into that source. You've got 2 check valves in series, plus a low-pressure drain before them, and a vacuum relief valve.
And you need to check these often.
Before every single use. Make sure the check valves close tightly. Make sure the drain opens when the pump stops. The vacuum relief is important too. It lets air in when the water stops flowing.
Why let air in?
To break any vacuum, a vacuum could suck the chemical backwards towards the water source. So letting air in prevents that siphoning.
Ah, okay. And the low pressure drain itself, where's that?
For those surface water systems, it's on the bottom of the pipe at the lowest point. So anything left in the pipe drains out automatically away from the water and gets contained.
Then there's the pump interlock. Sounds like a direct connection.
It is an electrical interlock. Irrigation pump stops, injection pump stops instantly. Simple, but vital. Prevents injecting chemical into a pipe with no water flowing.
Makes total sense. And a flow interrupter, another safeguard.
Yep. Usually a solenoid valve, electrically linked to the injection pump's motor. It sits on the inlet side of the injection line.
So it cuts off the pesticide supply.
Exactly. If the injection pump stops for any reason, this valve slams shut, stops pesticide flow, also stops irrigation water pushing back into the supply tank. Just make sure it's compatible with your chemicals and check it often.
Okay. And a flow sensor. What's that looking for?
It's watching the injection line itself. Is pesticide actually flowing? If not, maybe a hose is blocked, pump failed, tank's empty, it shuts down the injection pump. Another layer of protection against things going wrong.
Seems like a lot of redundancy, which is good. And one more check valve at the injection point.
Right where the pesticide enters the irrigation line, a spring-loaded check valve. Its job is purely to stop irrigation water from forcing its way back up the injection line into the tank. Needs about 10 psi to open, usually.
And a strainer to catch debris.
Yeah, simple but necessary. Sits between the supply tank and the pump. Stops grit or particles from clogging the pump or valves. Mesh size depends on the pesticide you're using.
Finally, the freshwater faucet. Where does that fit in?
Needs to be installed before the main backflow preventer, so the water's definitely clean.
And protected itself.
Yes. Needs its own backflow protection, like a hose bib vacuum breaker. And crucially, label it clearly, non-potable water.
What's it used for then?
Cleaning gear, rinsing empty containers, adding water to the supply tank for mixing.
What should it never be used for?
Never for injecting pesticide directly, and absolutely never as a source of drinking water. Very important distinction.
Wow. Okay, that covers a lot of ground. It's really clear that setting up chemigation isn't just, hooking things together. There's a lot of thought in the design and safety.
There really is. Proper design, choosing the right kit, and making absolutely sure all those safety devices are in place and working correctly. It's all essential. For the crop, yes, but absolutely critical for protecting our water.
So thinking about all this complexity and the potential risks involved, it does make you wonder, what's next? What kinds of innovations could make chemigation even safer, maybe more efficient in the future? Definitely something for you to think about after this deep dive. Thanks for tuning in.